Let's turn our attention to torsion. What is torsion? Well, it's basically just a force couple, or it's a twist or rotation. It's something that causes a rotational moment, a twisting moment, or as I said, a force couple. This is typically observed in things like power transmission, when you have torque being transmitted along the length of the shaft. Of course, the thing rotates at a certain speed, so anytime you have rotation, you probably have some torque along with it, unless it's just a system that's coasting down. You can imagine torque as considering a wrench. You probably all use this, where you've got a force offset at the end of the handle twisting a bolt or nut or something, and the amount of torque applied by the wrench is the amount of force you apply on the end of the wrench times the length of the wrench handle, which is shown as D in this picture. Now, there is a relationship between torque, power, and speed. Power is really how much energy goes into something per unit time in the form of work. At least in our case it will be work, because we're talking about torque times speed. Torque times speed is power, and you have to be careful of the units. There are some convenient conversion factors. In SI units, the power units are watts, and so torque has units of Newton meters or joules. Now, it's not really right to say that a torque has a unit of a joule, because a joule is for energy, whereas a Newton meter is for torque. But since we have to have rotational speed in radians per second to make everything consistent, a Newton meter per second, torque times speed, is a watt, and it's a joule per second. So it almost looks like a joule is a Newton meter, and it's true that force times distance is work. So however you want to think of that. The point is that in SI units it's pretty easy. You just have to make sure that the rotational speed is in radians per second. So if we take 68 kilowatts and 600 RPMs, what would the torque be? What do you have to do to figure it out? Well, I'll grab my calculator and go through it with you. The key is to realize that we need, instead of revolutions per minute, we need radians per second. So let's see, 600 revolutions per minute. To get radians, we need to multiply by 2 pi. So 2 pi radians per revolution. That gets rid of the revolutions. And then we have 1 over minutes. So what we need is 1 minute per 60 seconds. So we've got to divide by 60. And so I have a rotational speed of 62.83 or so radians per second. That's the number that I would multiply by the torque to get the power in watts. Now, notice I was given power in kilowatts. So since power equals torque times speed, what I can calculate from this, of course, is what's asked for, the torque. I will simply take the power, which is 68,000 watts, and divide it by 62.83 radians per second. So let me invert and multiply by 68,000. And if I did everything right, that is a torque of about 1,082 Newton meters. Well, here's a conversion factor, so that if you want power in horsepower, you want torque in inch-pounds, or pounds force inches, and speed in RPM, just divide by 63,025 on the right-hand side, and you'll make your units consistent. That's the conversion factor to take care of all those conversions. So something worth remembering. A lot of people will round this off to 63,000. But 63,025 is closer. It's not exact, but it's close enough. Now let's talk about what goes on when a member is twisted. Anytime you have a twisting type motion, the entire body twists. So imagine a line drawn straight on a cylinder, and then you twist that cylinder. Well, that line is now at an angle. Now, the angle between the original line and the new line along the length of the cylinder is given the symbol gamma. And that angle is, of course, related to the angle of twist out at the end of the rod. So if we got two ends of the rod like this pin here, okay? So two ends of the rod, if I hold one still and twist the other, there's going to be an angle of the twist on this end, and that angle we will give the symbol theta. Now, theta and gamma are related to each other, and we'll see that a little bit later, but they're related based on the radius and the length of the particular rod at hand. But what you really need to understand is this causes shear stress. Imagine it. Just imagine taking a shaft like this and holding onto it on one side, clamping on and clamping on the other, and then twisting. Now we're talking about shear stress occurring in a very small segment of the shaft here, our make-believe shaft. And you can imagine that that's where all the deflection is going to happen. But if I make that length a zero length, you can see what I'm trying to do is literally just shear the two halves of it. And so it should make sense that there would be a shear stress if you consider an element at the top or the bottom or any outside position, it should be clear that there's a stress, a shear stress on the back side of it as I try to shear the entire cross section. Of course, that shear is the same all the way across or all the way around the shaft, but it should be apparent that if we look at a stress element that's just a 2D stress element laying on the top of that shaft, that that's going to be a shear stress that's occurring. Now, of course, that shear stress is related to the torque we're applying. How are they related? Well, this is our first non-uniform stress profile. As a matter of fact, the way to think about stress profiles is that it should tell you the stress at every point on the area. So if you look at this circular area and you wanted to draw the stress profile on the vertical line instead of the horizontal line, it would look just like the one you see, but rotated 90 degrees and then rotated back 90 degrees. That's along that entire vertical line. That's what the stress profile would look like. In other words, you could rotate that stress profile you see there at any angle and it would be the appropriate stress profile for shear. Now, how do we know this? Well, you know it from solving differential equations where there are boundary conditions. In other words, there are conditions that at the center there can't be any torque. I'm just going to explain it in English rather than in math. There can't be any torque, right? It's a point. There can't be any force. And so it has to go down to 0 in the center. And through some reasoning you can figure out that the stress has to be maximum at the outside surface. And then again, through the solution of the differential equation you end up writing, you can find that it's just a linear distribution of shear stress within this circular area. So don't worry too much about how we've arrived at the stress profiles. Just try to remember the stress profiles for the different sections. They're usually about the same, and the most important thing in this class is sharpening your intuition. So we're not trying to develop a stress profile for any arbitrary cross-section. That's not our goal. That's the goal of deeper engineering, and we just want to understand how this works. So that it turns out that even in deeper engineering or trying to solve differential equations, most of the time you can't solve the differential equation unless you have a special shape, say a triangle or something like that, and even then it can be very difficult. And so what's the point in being able to solve, theoretically solve every problem out there? There's no point. We may as well just perform finite element analysis with some understanding of the basic concepts of stress and be able to solve problems more quickly and accurately anyway. So how do we calculate the maximum stress? Well, it turns out it's related to the maximum torque, of course, applied. The larger the torque, the larger the stress. That makes sense. It also depends on exactly what radius you look at. Remember, we had a linear stress profile, and the farther out on the radius of that shaft you go in the cross-sectional area, the higher the stress. Now, in this particular formula, this is the one you'll see most often. It's TC over J, and it gives you the maximum stress, which is at the outer fiber, right? The outer section of the shaft. J is called the polar moment of inertia of area, and it's just an area property in a certain direction, but we'll look at that a little bit later. For right now, you just need to know how to compute them. As a matter of fact, circular cross-sections are one of the most commonly used cross-sections for shafting, and that's where this idea of shear stress in shafts under torsion is really primarily used. So the geometry factor, or polar moment of inertia, J, is pi d to the 4th over 32, and where d is the diameter of the circular cross-section. Now, this only works for solid cross-sections. If you have a hollow cross-section, you have to change the equation a little bit. Now, if you want the stress at any point within the cross-sectional area, then you basically have to scale the maximum stress by whatever radial point you want versus the outer radius. An easier way to say this is you can simply calculate the stress at any point as TR over J. Just plug in the radius that you want, and as long as there's material there and it's a round section, then that would be the stress at that particular radius. Now, this formula for relating shear stress to torsion is only valid in the linear region. So we have to assume linear material behavior. In other words, that the material stretches reversibly, that there's no lost position, no yielding that occurs. So we're following Hooke's law. The same idea that you use when you've dealt with linear springs in the past. You never, I mean, in the real world, you've probably taken a little bitty linear spring and pulled it until it didn't return to its original shape. But in physics class, where you learned F equals kx, you never did that, right? You never talked about the point where that equation no longer holds, where there's yielding in the material. The other important parameter or consideration for this formula to be valid is that the material that the shaft is made from has to be isotropic and it has to be homogeneous. We can't have some varying material property or difference in behavior depending on the orientation. So a carbon fiber rod might not be modeled very well by that equation because it's a composite that will have different material properties in different directions. The other requirement is that we have to have a constant cross section in the area of the shaft that we're interested in. Now if you think about a hollow circular bar instead, it turns out that the stress is non-zero on that inner surface. It's still, the solution to the equation still is a linear line with decreasing stress from outer to inner, but the important part here is that we end up with some non-zero stress on the inside surface of that shaft. One thing about all of these profiles is they have to sum up essentially, in other words integrated over the total area, they have to add up to the load that's being applied because that's what resists the external load. Think about it again with this pen. If I hold onto this pen with one side, one of my hands, and then the other side, and I try to twist in opposite directions, let's say I could not slip, my fingers wouldn't slip. Well, in that case, I can imagine a free body where the material is cut in between my fingers. And so the material must have some kind of stress in it, and that stress is what has to balance the torque applied by the other hand. Imagine that we ghost this part out and this part of the pen out. Well, there's still torque being applied from this hand, and so the stresses have to add up to acting over that whole area in such a way that they generate an equal and opposite torque so that the material does not fail. So it's really important to keep that in mind as you're thinking about all these stress profiles. We've seen some simple uniform stress profiles, but those are pretty trivial. As we start to get into more and more complicated stress profiles, remember that the integration, the adding up of all that stress over the area just simply yields the load in the member at that point. Alright, so how much stress can materials take? Well, it depends on how they're loaded. And so what we'll usually do is use a so-called design stress that is the yield strength in shear divided by a factor of safety. Now a lot of times the yield strength in shear is not available, and so we have to use the yield strength in tension, and that can be calculated theoretically by taking the yield strength in shear can be taken or calculated theoretically as half of the yield strength in tension. Now that's not exact, but it's close enough for what we're doing most of the time. So if you look at the manner of loading, if it's a static or just steady torsion, then we don't really need a very high design factor. So we use a factor of 2, and so the factor we divide the yield strength in tension by, the 4 there, comes from the fact that we've got the factor of 2 for getting yield strength in shear, and from the actual factor of safety or design factor that we've chosen of 2. If it's a repeated torsion, in other words, if it's a torsion that's a fatiguing type torsion where it's applied and then released, applied and then released, maybe even fully reversed, okay, then we use a safety factor or a design factor of 4. And if it's a shock loading where the torque is applied very quickly, like a torque spike from a single cylinder engine, then we might use a design factor of 6 or so. Here's a screw that I yielded in torsion. I saved it for about a year before I finally took a picture of it and included it in the slides. And it's interesting because I was screwing the thing in, and this is made out of stainless, and it turns out that this stainless has a relatively low yield strength. So I was trying to screw the thing in, and I think it just wouldn't sink for some reason. I've forgotten why it was now, or even where it may have been using it on a door frame or something, I don't recall. But look at the upper half of the screw. And you'll notice that we're looking at the body section. It broke in the threads. That makes sense. That's where there's the highest stress concentration, the smallest diameter of material available. So that makes sense. But you can see that I was actually screwing it forward, right? Because it was going in right-handed, and you can tell that it yielded in that sense. Because look at on the shoulder, basically that solid section that's sort of bent. You can see some almost 45-degree lines in the image there. And those lines used to be essentially straight along the length of the shaft. So this thing really yielded along the entire length. And the reason I was able to do it is because you can't see it, but it's actually a Torx drive. And so the drive was not yielding and wasn't giving up. It was still driving the screw. And ultimately I broke the thing, realized what had happened, pulled out the broken piece, And I think I ended up actually sacrificing whatever I was working on to put some vice grips on the threaded portion to get it out and just look at it and see what had happened. Of course, the threaded portion you can't see in the picture, but it doesn't show any evidence of yielding. It was the screw was yielding basically from the threaded section up to the head. But there I definitely experienced the yield strength in shear of this material because the material was simply loaded in shear. Now the polar moment of inertia, if you're talking about a hollow bar, so think of a shaft that's hollow, looks a lot like that for a solid shaft. As a matter of fact, you simply subtract one from the other. Basically a solid polar moment of inertia minus a ghost polar moment of inertia for a solid that's missing, right? So that's the outer diameter to the fourth less the inner diameter to the fourth times pi over 32. Looks a lot like what we had before. And if you have shear stress, or if you want shear stress at any particular radial position, you have an equation now, a couple of them for calculating it, and of course coming up with a maximum shear stress is what we usually want the most. So tau max equals TC over J is usually the most important equation. Now it's a little bit inconvenient to deal with both the outside radius and the polar moment of inertia. The outside radius is of course the diameter over 2, so it makes no sense to have two separate numbers representing geometry of the shaft every time. We can put these two together. Notice that J over C appear very often in calculating the maximum stress. It's 'cause maximum stress is just TC over J, right? So if we put J and C together, notice that some of the things cancel out nicely, and we can create something we call the polar section modulus, Z sub P. And Z sub P then is just J over C. And in the case of a simple, solid circular shaft, Z sub P, the polar section modulus, is pi d cubed over 16. So that's a convenient thing to have. You should go to the back of your book now and look in the appendices and find where the polar moment of inertia for many different cross-sectional areas is given. There's a whole part of the appendix devoted to cross-sectional area properties, and you'll find this there as well as the equations for J. So then instead of writing tau max equals TC over J, we can write tau max equals T over ZP. We've just combined C and J. It's a little more convenient sometimes. Now what about if we compare two different shafts? One shaft, let's use the same general size, but let's make it so that they have the same polar section modulus. I'm sorry, I always forget the name of Z sub P. J I've got okay, the polar section modulus. That's no big deal. When I took strength of materials, we didn't use Z sub P. We simply used C and J. I don't know why, we just didn't. So I have to get used to that. So the polar section moduli, if we keep Z sub P the same for two different shafts, what happens? Well, what if we want to have the same maximum stress? Well, that would do it, wouldn't it? Because the maximum stress would simply be T over ZP, or T, the torque, over the section modulus. So putting the same torque on these two shafts that have the same section modulus will cause the same amount of maximum stress to be developed in both materials. So that's good because most materials have a certain maximum amount of shear stress you can apply to them, and that means we could make either shaft out of the same material and both shafts would do an equal job of carrying the torque. They'd yield at the same amount and probably fail at the same amount. But here's the thing. If you look at the area properties and you calculate, say you start off with a 50 millimeter shaft and then you start increasing, there's actually an infinite number of shafts you could theoretically design, but what if we put the maximum shaft diameter up to 60 millimeters and remove some material from the center then, while holding the polar section modulus this constant so that the maximum stress would be the same? Well, what you end up with is using about half of the material. So the amount of material required for the shaft on the right is about half that required on the left, and yet it can carry just as much torque because the material it's made from is stressed to the exact same amount. So what you find then is that it's actually better to make drive shafts hollow, right? That's better because you can reduce the weight. The material in the middle doesn't really help a whole lot. Why? Well, remember the stress profile that I showed you of the shear stress going from maximum at the outer fiber to 0 at the center. Well, what that means is that the material in the middle of solid shafts is not doing much to carry the load, right? What that means is there's just not much stress there, and so it's sort of wasted material. Why would we include that material when there's hardly any load to carry in that region? So if we simply eliminate it, then this ring, this annular region we have that remains for our cross-sectional area, this annular region is more uniformly stressed. Now it's still stressed higher at the outer fiber and less at the inner diameter, but more of the material carries a higher stress, and so ultimately that material is being used more efficiently. And that's why it's always beneficial to make drive shafts hollow. What about stress concentration? Well, it does occur in shafts. There's 4 different cases we will consider, and basically the way we will deal with these is to calculate the maximum shear stress using a stress concentration factor K, which we will have to look up in the back of the book, times the nominal shear stress, depending on how that nominal shear stress is defined. So go to the back of your book and look for shear stress factors as we go, or shear stress concentration factors, as we go through these various examples. And I've listed some of them in the slides as well. So what if we have a shaft that has a groove in it? Well, that groove is going to cause stress concentration. Shoulders, key seats, cross drilled shafts, anything where the geometry changes rapidly will cause stress concentration. And some geometry in shafts we don't have stress concentration factor tables or figures for, like we do for these particular ones. As a matter of fact, for a transverse hole, a hole that is drilled in order to usually locate a machine element hub for a gear or a pulley or sprocket or something, you can find stress concentration factors for torsion for this geometry in Appendix A22.5 on curve C. Now, a lot of times this sort of design happens when you match drill an element to the shaft. So what happens is you install the element where you want it, clamp them together, and just drill. And this often ends up with custom matched parts, but a lot of times you never want to take the two apart again, so it doesn't really matter. We use this at Amatrol in some of our drives going into robot harmonic gearboxes, basically harmonic drive gearboxes. And the reason was because we never wanted the motor, and it was actually an input gear or input bearing. We never wanted those two disassembled. We wanted the harmonic drive and the motor to be mounted and never taken apart, because you can end up with really bad vibrational problems if there's misalignment between the motor and the gear reduction box. And so we aligned them carefully and match drilled just because we never wanted them to come apart. So this is used, and of course it can be used too for parts that can be disassembled and reassembled and parts replaced. It can be used for interchangeable assemblies as well. You just have to drill the hole more precisely, and that has been done. That's fairly common as well. But the point is that this causes stress concentration in the shaft, and we have stress concentration factors for it. For grooves, grooves are often used when you want to seal a shaft or you want to distribute oil around the radius of the shaft. The key here to reduce the stress is to make that radius at the bottom as large as possible, as long as it's practical. And sometimes it's not. Sometimes you need a sharp corner there, and in that case the stress concentration is just going to be higher, and most likely that's a point where failure in the shaft can occur. So we've got stress concentration factors in Appendix A22.6 for this type of geometry as well. Now notice that the nominal stress for this shaft is based on the smaller diameter, the diameter at the base of the groove. So it's really important that you know that diameter in order to figure out the correct stress concentration factor magnitude. Sharp corners or sharp steps are also problematic. Again, large stress concentrators. And here the nominal stress is always based on the smaller diameter section after the step. Sled runners are a type of key that can be made in a shaft, and we're going to use 1.6 for those, and for profile key seats we're going to use 2.0. Now these are not terribly precise numbers. I would not recommend that you practice with these numbers. If you're going to design something, get some better stress concentration factors, because stop and think about where the largest stress occurs. Well, it occurs where there's the sharpest corner. Well, okay, where's the sharpest corner? Well, it's certainly not that generous radius that the cutter cuts out of the sled runner, right? And it's not really the ends where the end mill has cut out that fairly tight, but technically it's fairly loose, end of the key seat. Rather, it's in the corners, right? It's in the little corners, the oval shape. Well, it's not an oval, but the straight line and then semicircle at the end. It's in those bottom corners and at the bottom where the key sits way down. And similarly on the sled runner, that's where the main stress concentration occurs. So there are actually tables of stress concentration factors for these geometries as a function of that really tight corner radius, but it's a little more than we want to get into for this course. It's not really important that you understand or know what the actual numbers are right now, so we will simply use 1.6 and 2.0 for two different types of key seats. So now let's talk about deformation. We've talked about stress, but what about the way that the material changes shape? Because one of the things we're always interested in this class is load versus deflection. So how much load causes how much deflection, and the nature of that. That's why from the very beginning we start to take materials and pull them apart, and we don't just measure the force required to pull them apart, we measure how much they stretch in the process. So that deformation to load relationship is something we're really interested in. So now let's explore the other half of it, which is deformation. Now you can see the deformation in this case, gamma or theta. They are related to each other, but how does that relate to the torque applied? Well, here's the angle of twist due to an applied torque. So theta equals TL over JG. There's J again, the polar moment of inertia of the cross-sectional area. G is the material property we've learned about before. It's the shear modulus. T is the applied torque, and L is the length of the shaft. And then theta is just the amount of rotation at the end of the shaft. Now there's some things you need to know about this. First of all, we could rearrange it a little bit. Why don't we put the J, G, and L on the other side? What are they? Well, J is a geometry thing, L is a geometry thing, and G is a material thing, right? So they have nothing to do necessarily, well, not directly. They aren't the applied load, nor are they the deformation. They do all contribute to the stiffness, right? G is like a material stiffness, whereas J over L is like a geometry stiffness. But let's rearrange so that we have essentially deflection, although it's an angular deflection. Deflection times some constant equals the applied load. Now, if we write it more like a linear spring, because remember this equation only works when we're assuming linear behavior, then everything in the parentheses could be written as some spring constant, some effective spring constant K. And then it begins to look a lot like something you've seen before, right? Deflection times spring constant equals force, and you probably have been presented, have had this presented to you this way: force equals Kx, where x is the deflection and F is the force to cause that deflection. In the same way, T is the load and theta is the deflection that is caused by the load. Now K, in the case of F equals Kx, is a stiffness, right? And it has to do with the material that the spring's made of as well as the geometry of the spring. And in the same way, for these torsional springs, J, G, and L are all geometry or material stiffnesses, essentially. Now, one thing that's important, the angle of twist theta has to be in radians, but so does gamma. Both of those have to be radians for this to make any sense, and especially for the last equation because it involves theta directly. Now, if you have a shaft that, say, has a large section and it steps down to a smaller section, then steps down to another smaller section, you can actually calculate the total deformation out at the end by calculating the deformation of the first little section, the deformation of the second, and the deformation of the third, and just adding all three of those together. So you get a little bit of twist. Say you've got a thick shaft at the beginning, a medium shaft in the middle, and then a small shaft at the end. If they're all the same length and have the same material properties, then the first section, the really thick section of the shaft, won't angularly deflect much. It won't contribute much theta to the overall rotation of the ultimate end of that shaft. The center, which was a medium diameter, will contribute more. It will stress more, or I should say it will strain more. because the angle of twist will be higher in that section since you have a lower diameter. And then in the last section where you have a really small diameter, that's the section, assuming it has the same length as the other two, that will change angle and deform the most. Because remember, all three sections are carrying the same load if we're just grabbing either end of it and just torquing it, right? So we've got a thick section, a medium section, and then a small section at the end. So we can just simply add all of those theta deflections, the way they respond to the load in the material, and calculate the angle of twist as the sum. Now the shear modulus relates the shear stress to the shear strain. So G, remember, the shear modulus is related to the elastic modulus through Poisson's ratio, but what you really need is values of the shear modulus, and there's a table in your book that has several for a range of materials. Now there is a recommended maximum amount of twist for different applications. So how much twist should you allow per length of shaft, per inch of shaft, or per meter of shaft? Well, this is a table that gives you some recommendations for many different types of shafting. And so for high precision you want less torsional deflection typically, whereas for just general parts more torsional deflection is allowed. What about if we have a non-circular section? So far we've talked about round shafts and hollow round shafts. I mean, this has not been a particularly riveting movie, right? There aren't very many characters here. So what about other sections? Well, actually, a circular cross-section is the stiffest cross-section. And the closer a section becomes to a round section, the stiffer it becomes. And so things like pipes, solid square bars have decent torsional stiffness. Rectangular tubes, closed sections in general have fairly high torsional stiffness. But sections that are long and thin are very weak in torsion. So things like channels and angles are not good torsional members. So it's important to know that and not design a shaft that's made of an I-beam or something. Now, what if we have a non-circular section? Then what do we do for J? Well, for some sections we can calculate the polar moment of inertia fairly easily. It turns out it's an actual integrated thing. It's integrated over the area, but you don't want to do that. So we have several values or formulae for the polar moment of area, and they're listed in the back of your book in the appendix. Make sure you know where they are, as I mentioned before. It's that page that has all the cross-sectional area properties is well worth tabbing. But how do we calculate the maximum shear stress in this case? Well, what we will do is we will use the polar section modulus, I think it's called. As I said, I don't remember the name of ZP very well. That's what we will use, because think about it. If we tried to use TC over J, we might know J, but what is C? C is supposed to be a radius, right? And it doesn't work. It turns out the equation just doesn't work anymore. We can't use TC over J where we just have some radial distance to say if we have a triangular section, what's the radial distance from the centroid? Well, the equation doesn't work anymore. We have to combine C and J into the polar section modulus, ZP. Okay. Now, for the angle of twist, we can still use J. We can still use the polar moment of the area. But for the maximum stress, we can't. Now, to help us out, there's another page in your book that needs to be tabbed. It's near the end of chapter 4, and it looks like this. Now, let me warn you. Look in your book and make sure that the chart you have matches this. Several of the charts that I've seen in some printings of the books do not have the blue dots that I've got here to show where the maximum stress occurs. You might think that the maximum stress for the square, for example, would be farthest away from the center. Turns out it's not. It's on the face, the center of the face. Now understand that all of these are extruded out toward you, okay? But anyway, some printings of the book don't have the dots to indicate where the maximum stress occurs, and it's important that you know that. So make sure you've tabbed this page, make sure you're familiar with this. Another thing that confuses students has to do with the shaft with one flat and the shaft with two flats. A lot of times students make this mistake. It's a really easy mistake to make. To calculate the polar moment of inertia, J, or the polar section modulus, EP, you need the values of C1 or C2. Okay, no big deal. You can see there's a table off to the right where C1 and C2 are listed. You just need to know the ratio of H over R, where H is the height from the center to the flat, and R is the radius without the flat. That's pretty easy. So you calculate that ratio, and sometimes you have to interpolate. Obviously, the smallest this would be is 0, and the biggest the ratio would be is 1, because the flat's either going to end at the center of the shaft, or it's going to go all the way out and not be a flat. But anyway, students will look at this and they'll say, okay, no big deal. I can see how I would come up with a value for C1 or C2. Now here's the problem. Notice that the shaft with 2 flats has different levels of H over R. Look at it carefully. Notice it does not start at 0. It starts at 0.5 and goes all the way up to 1. And the mistake students sometimes make is they'll read off H over R from the very top of the chart, which is a natural thing to do because the rest of the data just looks like, you know, it's just data. It's a constant that you're trying to find. But actually the H over R row is repeated and they are different values, so be very careful about that. I think your author tried to make it obvious by making it C3 and C4 as the other constants that go into the equation, but I've had students mess up on this more than once, so I thought I would mention.